Hey everyone, today we are going to be solving problem 3.9 in the book. And this problem is kind of a continuation from example 3.2, so we're going to be using the results from example 3.2 to help us in our problem. So in example 3.2, it deals with a conducting sphere with a charge placed outside of it, a distance of a, and the sphere is grounded. So the potential on the surface of the sphere is 0. And so the way the book solves this is it places a charge q prime on the inside of the sphere at a distance b from the center, and the magnitude of q is, or q prime is equal to this. And the distance it's placed at is this, b, is equal to that. Right. And so to solve the potential on the outside of the sphere, the book uses the law of cosines as well as this triangle, and it solves it here. Right, so since we know that the sphere is grounded and the potential at the surface of the sphere is 0, we would expect that if we plug in r, which is the radius of the sphere, into these little r's, that we would get 0, and indeed we do get 0. So that's not what we want for our problem. For our problem, we want there to be a potential of v naught on the surface of the sphere, not a potential of 0. So the sphere is not grounded. So what do we do? How do we do this? So we can actually use some of the results from the example to help us solve our problem. So I've redrawn the sphere with the charge inside of it and the charge outside of it. And so we know that the potential on the surface of the sphere, right here, we know that that's equal to 0. We also know that the potential at that point is equal to the sum of the potentials due to these charges right here. So if you write that, we have that the potential is equal to the potential due to q plus the potential due to q prime. And since we're talking about the surface of the sphere, we know that those two potentials add up to 0. So that means we can place a third charge somewhere, anywhere really, like here, or there. And the potential on the surface of the sphere will rely only on that charge that I place. So in order to make things easier for ourselves, we can just put that charge in the center, since it makes it easier to relate to the other charges, which will be useful for us later on. So the potential at the surface of the sphere, due to this q double prime at the center, is just v sub q double prime. And since the other two potentials due to these other charges cancel out, the potential is just at the surface is just equal to v q double prime, and we can just call that v naught in our case, since that's what we want. So if we solve for that potential, we find that it's equal to this, and since we place that charge at the center of our sphere, we find that the r is just equal to the radius of the sphere. Since we're talking about the surface of the sphere, that's where we want the v naught to be located at. And since the problem is asking us for the charge, we can just solve this equation for q double prime, and we're left with this. So whatever potential that we want on the surface of that sphere, we can just put it here, and we can figure out what charge we want at the center. So that's the first part done. The second part, it wants us to find the force of attraction between a point charge and a neutral conducting sphere. So what is a neutral conducting sphere? That just means that the charge on the sphere is 0, right? So I've redrawn this over here. So we know what the force on a charge is thanks to this equation here. The force is just the magnitude of that charge times the electric field at that point where the charge is situated at. And so what is the electric field at this point where Q is? That is just this. So, oops, they should have a hat. So the electric field at this point here where Q is equal to 1/4 pi epsilon naught times the charge on the sphere, which is Qs, over the separation, r squared. So the separation between Q and the sphere times r hat. So, all right, so that's our E field. Let's just solve for E. So Q on the surface of the sphere is 0. Okay, so that means our E field is equal to 0. So that means our force is equal to 0, right? However, this is not the case. Since we know that a charge next to a conducting surface will induce a charge on that surface and will cause some force to occur. So this isn't right. So what do? How do we solve this problem? So what we can do is we can use the second uniqueness theorem given to us by the book, and that theorem is this. So if we have a region labeled V, and within that region we have several conducting bodies, as we see here, these little squiggles, and let's say that we have a known charge on each of these bodies, so Q1, Q2, and Q3. And let's also say that within this region we have a known charge density of rho, right? So the uniqueness theorem states that if we know those two boundary conditions, which is the charge density in the region and the charge on each of the conductors, which is, Q1, Q2, Q3, if we have those two boundary conditions, then the electric field within the region is known, has a unique solution, right? So the E field, due to these conductors, drawing them out, the E field has a unique solution. So how does that apply to our problem? So we can say that our, system with a sphere and a charge is within a region, let's say it's called R, region R, right? And let's say that in this region there is a known charge density rho. So we don't actually know the charge density, but we'll find out later that we don't actually need to know the charge density. Let's just say we do know it for the sake of this problem. And we also know the charges within this region since it's given to us, right? We know that the charge on the sphere is equal to 0, and we know that the charge Q is just Q. So that means that there is a unique solution for the E field in this region. Okay, so how does that help us? So we know that a unique solution for the E field only depends on the charges and the charge density in that region. So we only care about the charge on the surface of this conductor. So that means we can fill this conductor with any kind of charges, with a bunch of charges or whatever we want, as long as the surface of this conductor, of the sphere, is 0, then the same unique solution would apply as if there was nothing inside the sphere and the charge is 0. So that means we can bring in our charges from the last part, Q double prime and Q prime. And since we know from Gauss's law that charges within a conductor will induce a charge on that conductor, and as we see here, we want the surface or the charge on the surface of the conductor to be 0, we can say that Q double prime plus Q prime equals 0, right? So essentially what that means is Q double prime is equal to negative Q prime. So now we can solve the electric field since we know what the charge on the sphere is in relation or as the sum of other charges, which are not 0. So we can do that. We can substitute. We can substitute that into this equation here, and now we're left with this. So script r squared. So script r is just the separation between the charges and the point that we are finding the E field at. So we can rewrite this as q double prime over r squared plus q prime over r squared. And now we can just find the separation from these two charges. So in the case of q double prime, we know that the separation is just a from our diagram. So that's just going to be a squared. And for q prime, we know that the q prime is situated a distance b from the center. So that means that the separation here would just be a minus b squared. And so we can put everything together and we find that the electric field is, equal to this equation here. And since we know that q double prime is equal to the negative of q prime, right, we can just substitute that in and then factor out the q prime, and we're left with this. So this is the E field at the point where the charge q is located at. So now we can find the force. So the force is equal to the charge times the E field at that point. And we can just substitute in the E field that we found, and we have this. So last thing to do is, we know what q prime is, and we know what b is, since we were given that at the beginning, thanks to the book. So that's here. So we can just substitute that into our problem. And after a bit of algebra and manipulation, we find that the force is equal to this. Oh, actually, there should be a R ahead there. And so we see that there's a negative sign here, right? So since the book is asking for the force of attraction, we can just omit the negative sign since the force is in the direction of the sphere. So then this is our final answer. Thank you.